as usual, can somebody tell me what we're talking about? What's the subject? What's the topic? What concept have we been talking about? Just to wake you up a little. Dot product? Well, the dot product was a little bit a while ago. But yeah, I mean, in general, we're talking about the dot product. We're talking about the dot product because it tells us about perpendicularity, right? About orthogonality, right? Can somebody be a little bit more recent? Anybody? Yes, Lucy?
Orthogonal complements.
Orthogonal complements, yeah, that's exactly the topic. Right? So, orthogonal complements. So we're talking about the orthogonal complement of a subspace, right? Of a subspace of Rn. Right, so you have some subspace as a subspace in Rn, right? And we define this thing called the orthogonal complement, denoted as perp, right? What was the orthogonal complement? Somebody remember? Anybody remember? Maybe remember Julie, yeah.
It's the set of all things that is perpendicular, or it's perpendicular for each thing.
That's right. So it's a set of all elements of, let's say, of Rn, right? Set of all vectors in Rn such that x is perpendicular to every element in that subspace, right? The set of everything that's every vector that's perpendicular to every vector in S. Every vector in Rn that's perpendicular to every vector in S, right? I don't know if that's good English, but let's say that. Every vector in Rn that is perpendicular to every vector in S. Okay, and then we had proven a couple of small facts about these subspaces. We had said that one, that the dimension of the subspace plus the dimension of the orthogonal complement equals the dimension of the ambient space, right? N, right? If we're in Rn, right? And then the second thing was that we showed that if you have two bases, right? If V1 through Vr is a basis of S, and Vr plus 1 through Vn is a basis of S perp, then you can put them together, right? You can put them together, and that is a basis of Rn. Okay, right. And that is where we stopped, right? Okay. I hope everybody remembers that. Okay, so let's go on. Right, this is the first idea in this section, and then the second concept is something called a direct sum. Something called a direct sum. Okay, so here's the definition. It's kind of an odd one. So you have U and V that are subspaces of W, a vector space. You have a vector space, and then inside it you have these two subspaces. Okay. We say that W equals U direct sum V. Okay. W is, in English, that W is the direct sum of U and V. Okay. If every vector in W can be expressed uniquely. Every vector can be expressed uniquely as W equals U plus V, where U is in U and V is in V. Oops. As a sum W equals U plus V, where U is in U and V is in V. Okay, so in other words, everybody in W can be expressed as a sum of something in U and something in V, right? Everything in W can be broken down into something in U plus something in V, and that can only be done in one way. There are not two ways to do that. Okay, so just to make it concrete, let's give an example. Let's say that U is the span of 1, 0, 0, and V the span of 0, 1, 0, and 0, 0, 1. Right? The x-axis and the yz plane. Right? Got the x-axis here. You have the yz plane. Right? You have the yz plane here. Right? And anybody, so our W is R3. And you see that anybody in R3 can be expressed as somebody in U and somebody in V. And there's only one way to do that, right? Anybody in Rn, right? Anybody in Rn can be expressed as somebody in U, right? So there's somebody in V here, right? So this is our W vector. There's going to be somebody in V, and there's going to be somebody in U, a vector in U, right, this guy, which we can draw over here. Right? There's somebody in V and there's somebody in U that add up to W, and there's no other way to do this. Right? There's no other way to break this up. Okay, for a non-example, right, if we make U the span of 1, 0, 0, 0, 1, 0, and V the same thing as before, right, so we have now the xz plane, I'm sorry, xy plane and the yz plane. Right. Well, we still have the property that anybody in R3 can be expressed as a sum of somebody here and somebody there, but now we've got multiple ways of doing it. Do you see that? Right. For example, right, we could express it this first way, right? But we could also express this as this vector in U, right? This vector in U and this vector in V, right? You could drop this guy perpendicularly down onto the xy plane, right? And so there's multiple ways of doing it, right? So over here, we do say that R3 is the direct sum of U and W. Here, R3 is not the direct sum of U and W. Okay, not the direct sum. Okay, so if you remember some notation from the homework, it's a sum. R3 is the sum, but it's not the direct sum. Okay, so the direct sum is a little bit better, right? You have to have this uniqueness, quality of uniqueness. Okay, so I hope you're starting to get this peculiar idea of a direct sum of taking a vector space and breaking it into a direct sum of two subspaces. Okay, this may seem kind of weird and abstract, but in the next section we'll be doing something called the method of least squares. And this is exactly what we're going to need to pull off that really practical technique. Method of least squares was first introduced by Gauss when he, if you read your textbook, introduced by Gauss when he wanted to predict the position of a certain asteroid. So there were a bunch of people caught sight of an asteroid, and on 2 occasions they caught sight of the asteroid. The great astronomers of the day said, on such and such a date, it will appear at this place again. It'll appear at this place, and everybody was making guesses as to where the asteroid would appear. But Gauss said, "You're all wrong. It will appear here," and he chose a place that was completely different from everybody else. And lo and behold, it appeared where Gauss said it would, and that sort of like cemented his reputation as an astronomer, I think. Anyway, so he used this method of least squares. And this method of least squares is actually like the beginning of machine learning. If you've undoubtedly heard this term, machine learning. Okay, so yeah, so it seems like really abstract, but this is actually something extremely important and quite practical. Okay, so one thing you might notice over here is that these guys. That this U and V are actually orthogonal complements of each other, right? And it's actually true in general that, so in fact, in general, in this theorem, that given any subspace S in Rn, we can decompose Rn into S, into a direct sum of S and its complement. Okay, so we have to show two things, right? We want to show that one, every vector in Rn can be expressed as somebody in S, like somebody in S, and somebody in, well, let me use X, or let me use W here, sorry. Every vector W in N, Rn, can be expressed as somebody in S, as U plus V for some U in S and some V in S perp. Right? And the second part is we want to show that there's only one way to do it. This decomposition can only be done in one way. Right? In other words, that if U prime plus V prime also equals W, then U prime must be U, and W prime, V prime must be V. Right? If there's some other way to break this up, into something in S and something in S perp, right, so U prime is in S, V prime in S perp, then they must be the same way. Okay, so let's think about that, right? We're saying that you have a orthogonal. I'm sorry, you have a subspace. You have an orthogonal subspace, right? And you're saying that the whole space in Rn can be expressed. Everybody in Rn can be expressed as something in S and something in S perp. Okay. That actually, that actually you can probably explain to me. So think about why is that true? Why is it true that if you have something in Rn, it can be expressed as something in S and plus something in S perp? You know certain facts about S and S perp. It's basically a consequence of those facts. It's a consequence of one of the facts that we put up on the board at the beginning of class, basically. So think about it for a minute, and I'll come back after wandering around outside. Okay, talk to each other, please. Talk to somebody in your class. Okay. Anybody figure out this first part? Why is it true that anybody in Rn can be expressed as something in S plus something in S perp? We know something about S and S perp. Molly? Yep.
Together they form a basis of Rn.
Yeah. So we had this theorem that said that. So recall that, right? If we have B1 to BR and BR plus 1 Bn, basis of S and basis of S perp, then the union, right, B1 to Bn, B1 to Bn is a basis of Rn, right? Right. So you say, okay, well, look, as W can be expressed as a sum of these guys, right? Equals C1 B1 plus CR BR plus CR plus 1 BR plus R plus 1 plus R plus 1 plus CN right? For some C1 to CR to CN. Right? Because that's a basis for R, so this guy in R can be expressed as a linear combination, right? Okay, right. But then you say, okay, but look, this thing is in S, and this thing is in S perp, right? So there's a way of breaking this up into the sum of something in S and something in S perp, right? Just the first part and the second part. So yeah, that was the key to it. Right. Okay. Part two, you said, okay, well, look, there's sort of a funny thing you can do at this point, right? So if W equals U plus V and W equals U prime plus V prime, right? Where these, U and U prime are in S, V and V prime are in S perp, then you know that, of course, U plus V equals U prime plus V prime. You can play a funny trick that, does anyone see how you could show that U and U prime, that U minus U prime has to be 0? Why would U minus U prime have to be 0? What's U minus U prime? Well, U minus U prime is V prime minus V. Right? So, where is this thing on the left? In what subspace is it? Well, the U's are in S, so this is in S. So yes.
The only way that they're equal is if it's at 0.
Exactly. Right. So this is an S. This is an S perp. You have something, right, that is an S and an S perp simultaneously, right? And so it must be 0, right? So it must be the 0 factor, right? And thus U must be U prime and V must be V prime. Okay. So this will be pretty useful, right? That given any subspace, you can break up Rn into the direct sum of that subspace and its orthogonal complement. Any questions? Everybody following? Anybody confused? Anybody willing to admit being confused? No? Maybe that's what I should ask rather than, is anybody confused? Anybody willing to admit that they're confused? Okay, good. Or bad. Okay, so the next thing we're going to talk about is the orthogonal complement of the orthogonal complement. What do you expect? What do you think about the orthogonal complement of the orthogonal complement? Yeah.
I think it would be the original.
You think it'll be the original? Yeah. In fact, that's what happens. Okay. So as a subspace Rn, then the orthogonal complement of the orthogonal complement equals S. Okay, so we're going to prove that these guys are equal. So we're going to prove it in the way of saying, well, the right hand contains the left side. The left side contains the right side, and the right side contains the left side. Okay, so we'll do that in pieces. Okay, so maybe honestly think about it. Think for 1 minute, or maybe just 30 seconds, about why, if you're in S, you must be in S perp perp. If you're in S, you must be in F perp perp. So we want to say that if you have some V in S, then V must be in S perp perp. Okay, so you just have to think, what does it mean to be in S perp perp? Okay, talk to somebody nearby. Talk to somebody and say, oh yeah, sure.
I just want to fill in the basics. So we just see that S and S prep on the basis of R and S prep and S prep as the also.
All the records are for
Okay, so okay. So let's ask, what does it mean to be an S per perp? What does it mean to be the orthogonal complement of something? It means that you are one of the vectors who's perpendicular to everything in that subspace, right? So if you are an S, are you perpendicular to everything in S perp? Sure, because S perp is the guys who are perpendicular to S, right? So this is actually trivial, right? Right, so you just say, of course, right? Right. So, like if V is an S, then certainly V is perpendicular to every vector in S perp, right? That's how S perp is constructed, right? So V must be in S perp in the orthogonal complement of the orthogonal complement. So this is almost a tautology. Okay. The backwards direction, showing that S per perp is contained in S, is a little bit trickier. Okay, so you say, okay, suppose that you have somebody in S per perp. Okay. Suppose you have somebody in S per perp, and what we're going to do is take the direct sum. So we know that x equals u plus v for some u in S and some v in S perp, right? Because Rn is the direct sum of S and S perp. Okay. Right. So now if we take the dot product of V, so take this part V. Okay. Take this part V, which is in S perp. Okay. And take the dot product against S. Okay. Take the dot product against S. X. Excuse me. Take the dot product against X. What do you get? What do you get? V is in S perp. X is in S per perp. So the dot product is 0. Thank you. Right? Because V is in S perp, X is in S per perp. Right? X is in the orthogonal complement to the orthogonal complement. Okay? So you get 0. Okay. Is that okay? Nico, you look a little funny.
We're just gonna have to go over those.
Okay, that's all right. That's all right. I mean, the point is that we have something in a space and we have something in the orthogonal complement to that space, right? So they're perpendicular to each other. Okay. Okay. Now I'm going to rewrite this. This x is u plus v. This x is u plus v, so I get v transpose u plus v transpose v. Right? But remember where u is in S. U is in S, and V was in S perp. So this is also 0. Right? This is also 0. Right? But what does that tell us? That tells us that V transpose V, the dot product of V against itself is 0. Right? But what does that tell you about V? Let's tell you about V. Julie.
Well, if something dotted against itself is 0, it's either perpendicular to itself.
Yeah, it's perpendicular to itself, which means that it is
This.
0. Yeah, it has to be 0. Right. That is, I mean, I think maybe an easy way of thinking about it is that the dot product of a vector against itself is the magnitude squared. Right? So you know that the magnitude of your vector is 0, so it's a 0 vector. There's only one vector with magnitude 0. This tells you that V is 0. V is the 0 vector. Okay. Right? In other words, thus, our x is u plus the 0 vector, right? This v that we were playing with is actually the 0 vector, right? But that tells you that x must be in S, right? Because u was in S, right? X is something in S only. The part that was in S perp actually turned out to be 0. So in other words, we see that if you are in S perp, then you are contained in S, right? Anybody in S perp is contained in S. In other words, we have containment this going this direction. Yeah, Julia.
So the things that this is a silly question. The things
These
that-
guys?
Yeah.
Yeah, so this is
one way or the other, right?
Yeah, these are containment. So like, right, so A is a subset of B, A is a superset of B, right? In other words, B is a subset of A, right? So this is saying that A is contained inside of B, and the second one is saying that B is contained inside of A. Well, that can only happen if they're identical, right? To show two sets are equal to each other, we need to show, it suffices to show, I should say we need to show these two facts. Okay. Yeah, that wasn't obvious to me when I first entered college. We had to figure it out. I remember, I think on my first homework set, we were supposed to show something like this, and I only showed one direction, and of course it was marked off, right? I remember very clearly that first problem set. I spent 13 hours on it, and then got, I think, 37 out of 64. This was the class, I don't know if I mentioned this before, this was the class that started off with 70 students and then finished with 20 students. Okay.
Were you one of the 20?
Yeah. Yeah. That's how I became a math major. That's actually not how I became a math major. It was the course after that sort of got me, made me think that I might be able to do it. Okay. So now we're going to do something that puts all of this stuff together. So clarifying the relationship. Yeah, I was one of the 20, but it was not easy. Clarifying the relationship between, that is, I spent a lot of time in the library, between row spaces and column space. Row space and column space. Okay. So, so remember way back when we were talking about rank, so recall that we saw way back when that the dimension of the column space, right? So let me just write it in English. The dimension of the row space of a matrix equals the dimension of the column space of that same matrix, right? And we said we defined this number, whatever it was, to be the rank, right? In notation, this is saying that the dimension of the range of A equals the dimension of the range of the transpose. Okay? In our more sophisticated way of talking, this is what we say. the dimension of the range of A equals the dimension of the range of the transpose. Now we can actually explain this a little bit more clearly. Why does this happen? So think about the map T sub A. Consider the map T sub A. Okay. And suppose we let it act on the range of A transpose. Okay. It turns out that this will. So think of think of the image of this. Well, the image of this is going to be in the range of A, right? The image of this is going to be in the range of A, right? Because you multiply by A, right? So what you get out is in the range of A, right? You feed something into it, right? You feed some vector to it, right? And you get AX. Well, that's in the range of A, right? So this map T sub A goes from here to here. Okay. I claim that the map is an isomorphism. In other words, it is onto and one-to-one. In other words, the range of A transpose and the range of A are actually isomorphic to each other. They're basically the same subspace. Okay, so this is a little bit abstract. So try and get it. If you can't, that's okay. It may require further digestion outside of class. So it's like, here's this thing, you can try and eat it now. You may not be able to get it. That's okay. Chew on it later. I don't know if this is a good analogy, but anyway, I'm not sure if people will get this immediately. That's okay. So let's see if I can explain this well. Okay, so let's say that you have some matrix, and it's an m by n matrix. Okay, it's an m by n matrix. So when you talk about T sub A, that's a map going from where to where? Well, it'll go from Rn to Rm, right? It'll go from Rn, excuse me, to Rn, excuse me. Right? That's a map from Rn to Rm. Okay. Now think. The range of A transpose, well, A transpose is an n by m matrix, right? So A transpose goes from Rm to Rn, right? So the range of A transpose is in Rn, just to keep things clear, right? Everybody okay? We haven't said nothing deep at all so far. Okay. The range of A transpose is in Rn. Right? Fewer people are nodding. I hope doesn't mean anything. Okay. Right? So take a direct sum. Right? Rn we can express as, the range of A transpose plus the range of A transpose perp. Right? You've got a subspace, so you can decompose Rn into that subspace direct sum, its orthogonal complement. Right? This is your S, this is your S perp. Okay? Okay, but now, got RA transpose perp, right? RA transpose perp. RA transpose perp. This is something you've seen before. You know something about RA transpose perp. The orthogonal complement of the range of the transpose. Lizzie?
Is it the null space of A?
It's a null space of A by the fundamental subspaces theorem, right? We've seen this before, right? So this is actually the null space of A. Null space of A. Okay, so this this gives you some information. So notice this gives you some. This actually gives you information about how T sub A works, right? If X is in Rn, then X equals something in Ra transpose plus something in the null space of A. Right? If you're in Rn, then you're something in Ra transpose plus something in the null space of A. Right? Right? But then, when you get acted on by the matrix, what happens? Well, you get AU plus AV. But what's AV? AV is 0, right? AV is 0, right? So, part of this sort of gives you an understanding of how the matrix works, right? Part of it will just vanish, right? Part of the output just vanishes, right? And the other part is acted on independently. So this is sort of an aside, but it's a useful thing to keep in mind. Okay, so now let's see if I can explain to you why this thing is an isomorphism. Okay, so I'm just sort of setting up the background here, and now let's talk about the proof itself. Okay, so observe. TA from Rn to Ra is onto. Right? Because RA is the range of A, right? If we take everything in the input, well, that gives us everything in the output, right? So this has got to be, this is all you have, right? So this is definitely onto, right? This is an onto map, right? Because you're looking at everything possible you can feed in, and you're talking about the output of, this is almost by definition onto. This is the set of outputs, so definitely it's onto the set of outputs. Okay, but this Rn, remember, it is Ra transpose plus null space of A, as we just said, right? Rn is Ra transpose plus null space of A. So this is onto, of course. That's the same. We've written the same thing twice. as we seem to do a lot. Okay. But the null space of A doesn't contribute anything, right? So I can erase this. I can erase this part, right? This on the range of A transpose is onto, right? Because the null space of A just gives me 0 over here, right? So I don't lose anything. I'm still going to get the 0, right? There's a 0 in here, I get the 0 over there. Erasing this null space, it doesn't lose anything. Okay. So TA from RA transpose to RA is onto. Okay. So that's the onto part. Now we need to do the one-to-one part. Okay. So 1 is onto. 2 is TA from RA transpose to RA one-to-one. Since we don't have much time, I'll just do it. Let's say that U1 and U2 are in RA transpose, and that AU1 equals AU2. Remember what one-to-one means. It means that if the outputs are equal, the inputs are equal, right? So we're trying to see that U1 and U2 must be the same. You say, well, A of U1 minus U2 is 0. Right? A of U1 minus U2 is 0, so that means that U1 minus U2 is in the null space of A. Okay. But U1 minus U2 is in the range of A transpose, right? Because U1 and U2 are themselves in the range of A transpose, so their difference is in the range of A transpose, right? So that tells you that U1 minus U2 is in the range of A transpose, and it's also in the null space of A. So the null space of A is the range of A transpose perp, right? The range of A transpose perp, right? So that means that this guy lies in a subspace and it's orthogonal complement, and so it must be 0, right? U1 minus U2 must be 0. Right? So U1 equals U2. This is kind of a nice application of everything we did in this section. Right? The fundamental subspace theorem, the direct sum, and ties it back to the rank theorem and everything. Okay, that's it for today.